So friends, today we are going to discuss a new numerical problem which is based on the shear force and the bending moment diagram for this cantilever beam. There is a load 3W acting at the point D and there is a point load 2W acting at C and W is acting at B, and we have to draw the shear force and the bending moment diagram for this cantilever beam. So first thing is that we have to find out the net reaction force acting at the point A and the reaction moment acting at this point A. You can solve it without finding out the reactions at the point A also, but for the concept making I am solving it by finding out the reactions at the point A. So first we will find out the net vertical force acting over this beam. So the net vertical force acting is W plus 2W plus 3W will give us 6W acting in downward direction. And the reaction at the point A in vertical direction will be equal to this F net, and it will have the magnitude 6W, but the direction will be opposite to that of F net. That's why going in vertically upward direction. So the reaction at the point A in vertical direction is how much? 6W going vertically up. Now the net moment at the point A is how much? Because of this force there will be a moment of 3W into 3x. X plus x is 3x taken here, going in anti-clockwise direction, clockwise direction. Okay, because this load 3W is rotating this beam AD in anti-clockwise direction, clockwise direction about this point A. Similar is true for the point, these 2 point load also. So because of this 2W, there will be a movement of magnitude 2W into 2x, x plus x, 2x in clockwise direction, and because of this W, there will be a movement of W into x going in clockwise direction. All these three will add up to give us a moment of 14WX going in clockwise direction. So the reaction moment at the point A, denoted by this MAR, is equal to 14WX going in anti-clockwise direction, that is opposite to the direction of this 14WX is anti-clockwise direction. So the movement will look like this, going in anti-clockwise direction, and its value is 14WX. Now we will draw the shear force and the bend. Now friends, to find out the shear force diagram, we have to find out the shear force at the point A, B, C and D. We have to find out the shear force on the left side of the point A and on the right side of the point A, and on the left side of the point B and on the right side of the point B. Similarly, we have to do the same thing for the point C and D also. Okay. Now friends, the point A, at the point A, why we have to find out the shear force on the left side of the point A and right side of the point A, and similarly we have to do this thing also for B, C and D points also. Why? The reason is that on the left side, when we go from left side of the point A to the right side of the point A, then the shear force will change suddenly. That's why we have to find out the shear force on the left side of the point A and on the right side of the point A. Now we will calculate the shear force on the left side of the point A. For that we have to construct a section here on the left side of the point A. This is the section XX constructed here. Now looking on the left side of this section, we can see that there is no force lying. That's why shear force on the left side of the point A is 0. Now shear force on the right side of the point A, if you want to find out, then we have to construct a section here on the right side of the point A. This is the section XX constructed here. Now looking on the left side of this section, you can see that this force acting at the point A, that is the reaction force, is accounting for a positive shear force of magnitude 6W, that is plus 6W according to this sign convention. Okay, this is the section XX, this is our section XX, and this force is going in vertically upward direction with respect to this section XX, and this reaction RAB is also going in vertically upward direction with respect to this section XX in line on the left side of the section XX. That's why taken as positive. Now shear force on the left side of the point B we will calculate now. So constructing a section here on the left side of the point B. This is the section constructed here. Now looking on the left side of this section, this force will contribute toward a shear force of magnitude plus 6W using this sign convention. This moment will not contribute toward any shear force about this section XX. Now shear force on the right side of the point B. For that we have to construct a section on the right side of the point B. This is the section XX constructed here. Now looking on the left side of this section, this force is contributing toward a shear force of plus 6W using this sign convention, and this force is contributing toward a shear force of minus W using this sign convention. Okay, so it will give us 5W. Now shear force on the left side of the point C we will calculate. Now constructing a section on the left side of the point C, here you can see that this force is accounting for a shear force of magnitude plus 6W about this section XX, and it is accounting for minus W about this section XX, and it will give us 5W. Now shear force on the right side of the point C we want to calculate, then we have to construct a section here on the right side of the point C. Now looking on the left side of this section, this force is accounting for a shear force of plus 6W using this sign convention. This is accounting for a shear force of minus W using this sign convention, and this is accounting for a shear force of minus 2W using this sign convention. So it will give us 3W. Now shear force on the left side of the point D we want to calculate, then we have to construct a section here on the left side of the point D. Now looking on the left side of this section, this force is accounting for a shear force of 6W. This force is accounting for a shear force of minus W using this sign convention. This is accounting for minus 2W using this sign convention again. So it will again give us 3W. Now friends, shear force on the right side of the point D, if you want to calculate, then you can look on the right side of the section. Earlier we have considered the left side of this section XX. Now I am considering the right side of this section XX. On the right side of this section XX, there is no force line. That's why shear force on the right side of the point D is 0. Now we will draw the shear force diagram. Now friends, see this. At the point A, shear force is 0. So looking across here, on the right side of the point A, it is increasing to 6W. So making here 6W, making cross here above the point A at the distance of 6W. Now shear force on the left side of the point B is 6W. So on the same level above the point B, we will mark 6W. And our shear force on the right side of the point B is going to plus 5W. So it will decrease to plus 5W here above the point B. And it is going to plus 5W on the left side of the point C. So we will mark over the point C 5W in the same level of the 5W this cross. And shear force on the right side of the point C is going to plus 3W. Plus 3W will lie somewhere here below this point for 5W. And shear force on the left side of the point D is also equal to 3W. So making across here on the same level of 3W, and shear force on the right side of the point D is 0, making across here. So joining first point with the second, second with the third, third with the fourth, fourth with the fifth, fifth with the sixth, sixth with the seventh, seventh with the eighth, we will get our shear force diagram. Now friends, we will draw the bending moment diagram. Now friends, we will find out the bending moment at the point A. We have to find out the bending moment on the left side of the point A and on the right side of the point A. Why? Because there is a concentrated movement of magnitude 14 Wx is acting in anti-clockwise direction at the point A. That's why the bending moment will change suddenly when going from left side of the point A to the right side of the point A. That's why we have to calculate the bending moment on the left side of the point A and on the right side of the point A. And we have to calculate the bending moment at the point B, C and D directly. We do not have to calculate on the left side and on the right side of these points, because there is no concentrated movement lying at any of these points B, C and D. Now bending moment on the left side of the point A, for that we have to construct a section on the left side of this point A. This is the section XX constructed here on the left side of the point A. Now looking on the left side of this section, there is no force, no concentrated movement line. So the bending moment on the left side of the point A is 0. Now bending moment on the right side of the point A, we want to calculate, then we have to construct a section here on the right side of the point A. Now looking on the left side of this section, then this concentrated movement is accounting for a bending moment of magnitude this 14Wx having a minus sign. Why? Using this sign convention. Okay, because this is our section XX similar to this section XX, and a movement is going in anti-clockwise direction and lying on LHS of this section is treated as negative. Similar is true for this movement also. That's why it is taken as negative. And because of this reaction force RAB, there is no movement about this section XX, because this distance between the point A and this section XX is almost zero. Now bending moment at the point B we will calculate directly by constructing a section at the point B. So constructing a section at the point B and looking on the left side of the section XX, we can see that this force is contributing toward a bending moment of how much? The magnitude of this force 6W into this distance X, and it will contribute a positive bending moment which is sagging in nature using this sign convention. Okay, you can relate this thing with this portion of the diagram by using this section XX, this section XX, and this force acting vertically upward direction and this force acting vertically upward direction, creating a sagging bending movement similar to this thing. So the bending moment because of this concentrated movement will be equal to minus 14 Wx about this section XX using this sign convention. Now friends, bending moment we will calculate about the point C. Now bending moment at the point C, if you want to calculate, then construct a section at the point C. Now looking on the left side of this section, this force is contributing toward a bending moment of magnitude 6W into this distance x plus x, that is 2x, positive sign using this sign convention, and this concentrated movement is creating a bending moment of minus 14Wx using this sign convention, and this force is contributing toward a bending moment of minus Wx using this sign convention. So you will get how much bending moment at the point C. When you solve this, you will get a bending moment of minus 3Wx, and this value was coming out to be minus 8Wx. You should calculate this value yourself. Now bending moment at the point D. When you calculate the bending moment at the point D, then you can calculate very easily constructing a section here at the point D, passing through this point D. And now I will look on the right side of this section. Earlier I have looked on the left side of this section. Now looking in the right side of the section, you can see that there is no force lying on the right side of this section. No movement is lying on the right side of this section XX, so the bending moment at the point D is 0. You can do the same thing by looking on the left side of this section and considering movement because of this force, this movement, this force, and this force about this section XX. The result will be same, that is, it will come out to be 0. Now if we draw the bending moment, now see here, bending moment at the point A is 0, so making a cross here at this line, and bending moment on the right side of the point A is minus 14Wx, so making 14Wx here, minus 14Wx below this point A. Okay, now bending moment at the point B is minus 8Wx, so 8Wx will lie somewhere here, 8Wx, and bending moment at the point C is minus 3Wx, it will lie somewhere here, minus 3Wx, and bending moment at the point D is 0, so making cross here. So joining first point with the second point is joined with the third with an inclined line, because the shear force diagram is a horizontal line between the point A and B, so the bending moment diagram between the point A and B will be an inclined line. Similar thing we can conclude for the point between bending moment diagram between the point B and C, and joining third point with the fourth, you will get your bending moment diagram. Okay, so this was all for today's topic, friend, and if you like my video, you can subscribe my channel and also press the bell icon for the notification of the upcoming videos.